After showing you guys the full electric effect, and we looked at Compton scattering and the momentum attached to light, and even I showed you the pair production and annihilation, which really showed that whole mass as a form of energy type thing. Let's sort of put a few things together here and sort of summarize a little bit, because we've been talking about light, of course, and we're looking at light, is it a wave or is it a particle? And of course, that's the problem right there, is you think it's one or the other, but of course, it definitely shows properties of both. You can't just do one or the other. So, for example, if you look at the wave type stuff, you've got like Snell's law, you've got the refraction going on, you've got Huygens principle, you've got all these different things as wave type stuff that light can do. You've got things like the interference patterns, all these different things that are very wavy type things. So there's your wave type stuff. But now you've also got that whole particle type stuff, where we've got Planck's hypothesis, so Planck's hypothesis and quantized energy. You've got the photoelectric effect. You've got the Compton effect. You've got the Compton scattering. You've got the annihilation. You've got all those different things. They're all very particle type things. So which one is it? Well, it's not. It's sort of got both things going on. And I've sort of got this little picture that should look familiar to you in terms of basic electromagnetic wave, which of course is sort of how light works. Now, sort of how I like to think of it, what I found the best way to think about it for myself anyway, is when you talk about light, I like to think about it this way. You have a particle photon bundle of energy. Okay, so you have this little particle photon bundle of energy, and basically what it does is it follows an electromagnetic wave pathway. And this is the way I like to think about it. So when you're doing things like Snell's law, Huygens principle, interference patterns, when you're doing those wave type things, that is when you are manipulating and working with the electromagnetic wave type thing. So you're adjusting the pathway. And you've got this particle thing, you've got this little particle on there, you've got that particle, that photon on there that goes along for the ride. So when you adjust the pathway by refracting it or having an interference pattern or anything like that, when you adjust the actual wave direction, the wave pattern, that type of stuff, the photon then just goes along for the ride. So when you're doing the whole wave experiments, whether it's Snell's law or Huygens principle type stuff or the Young experiment and all that kind of stuff, you're messing with the pathway, you're working with the pathway, you're adjusting the pathway. So you're looking at the pathway type attributes of light. But then when you are doing things like the photoelectric effect or the Compton scattering or the pair production annihilation, where the actual having collisions and stuff like, well, then you're working with the particle nature of the light. And it's going along that wave pathway, but you're letting that particle thing slam into stuff. So if I go back to the diagram, you've got the electromagnetic wave. So if I start here, so between here and here, somewhere in this section here, you don't actually know where, there's a little bundle of energy called a photon. Between here and here, maybe it's over here. Between here and here, maybe it's over there. Who knows? Nobody actually really knows. But contained with every single oscillation, with every single full cycle wavelength, there's a bundle of energy contained within that one cycle of the wavelength called photon. I like to think about it like as a highway. So basically the electromagnetic wave is the highway. And the highway changes direction. It goes left, it goes right, it goes straight. It does what it does. And the cars and the trucks, all that kind of stuff on the highway are like the photons. These guys travel along that pathway. And if the highway curves left, well then that's the way the cars go. They sort of go along for the ride. So when you're doing different experiments, you are either, working with the highway, you're working with the path and making the path do different things, making it curl left or right or make bridges or whatever you're going to do with the actual pathway. But then when you're working with the particle stuff like the Planck's hypothesis and the photoelectric effect and Compton scattering, that type of stuff, Well, then you're messing with the cars. You're putting a wall along the highway and letting a car slam into it. You're working with the car type stuff. So it's not really that it's one or the other. It's a combination of both. And you either work with the wave nature, you work with the highway, or you work with the particle nature, you work with the cars and stuff like that, one or the other based on your experiment. Now, of course, this is where the whole idea of duality kicks in. The whole idea of duality, where it basically has both properties. Okay, it has particle properties and wave particles. It's not one or the other. But when you typically do experiments, you basically have to choose one in order to actually do any type of experiment. So if you want to choose to study the wave stuff, well, then you look at like Snell's law and the Young experiment, Huygens principle, that type of stuff. If you want to work with the particle type stuff, then do like the photoelectric effect type stuff, the Compton stuff. You have to choose one or the other. So that was actually an idea that really was proposed by Niels Bohr way back in the old days, that you have to accept that light has got attributes of both. But if you want to do an experiment study, you sort of got to pick one attribute or the other attribute. If you want to study cars, you don't go and research highways and what highways look like. You look at the actual cars themselves, the particle part. So that's sort of the idea of how these things sort of link together and the idea behind duality and that type of stuff. Okay? And it sort of summarizes and ties all this sort of type of stuff together. Now, of course, with this idea of duality and attributes of that type of stuff, this actually got extended a little bit even more in the 1920s with another really cool experiment that I'm just going to show you a little bit next. So we're sort of looking in the 1920s, like about 100 years ago. And basically what they've done is they sort of established that light is a wave with basically particle attributes is a good way to think about it. So one of the ideas that came out of this whole thing with the duality type of idea and that type of thing is if light is a wave that acts like a particle, one of the ideas that they had to sort of extend this, sort of reverse it. Remember, a lot of physics and science about symmetry, back and forth balance, and that type of stuff. And basically, if you've got light, you've got a wave that has particle attributes, one of the things they asked was, well, can particles have wave attributes? Can you actually sort of reverse this? Can you just take this and reverse this idea? So what they want to do is they want to say, hey, I wonder if we can get particles to have wave attributes. Now, one of the cool things about this is they want to see if they could actually test the idea and theorize it. Now, one of the things that they sort of did is, hey, what connects sort of like particles and waves together? And we sort of showed you before, one of the big things in the 1920s is they found out that, light actually has momentum. You just have to find it in a different way because you can't use mv. Light has momentum, of course, which was h over lambda. Okay, and that was just one of the expressions we had for it. But if we look at classical momentum, of course, is mv. Well, if the two momentums, if this p and this p are actually measuring the same thing, maybe we can tie those two things together. And if we just tie those two things together, we have h over lambda is equal to mv. And as soon as you do that, you've got two quantities that have never been attached together before, mass and wavelength. Mass and wavelength, those things typically have never been put together before, but it shows you how you could calculate the wavelength of something that actually has mass. And if we just rearrange it, lambda would just be h over mv. And this is what's often referred to as the de Broglie wavelength. And de Broglie might sound familiar from your chemistry class, but it's a way to calculate the wavelength of something with mass. Now, this only works if something has mass. If it has mass, you can't use this. Then you have to use just the basic light type stuff. So if it's got mass, you could actually calculate the wavelength for it. And so, well, that's pretty cool. But of course, this is the theoretical idea behind it. So what they want to know is, how could you actually test for this? How could you actually test to see if something with mass actually moves like it has a wavelength? Well, they came up with the idea of, could they actually take something and cause it to refract? Could you actually refract a mass, because refraction, of course, is a classic thing that light does when it goes from one material to another. So could you actually try and refract a mass? Take something with mass, have it change mediums, and then actually refract according to Snell's law. And you could actually use this then to calculate what the refracted angle should be. So they wanted to test this, and this was actually done by a guy named Thomson. He's actually the son of J.J. Thomson, who actually proved that the electron had mass and charge. What he did is they actually shot electrons at crystal. So they shot electrons at crystal because they wanted to see if they would actually refract, okay, which is really kind of cool. Now, of course, if you go back to the expression, remember the Planck's constant is times 10 to the negative 34. You need a mass that's unbelievably small to try and cancel out those powers of 10, and the negative 31 on the mass of the electron works really, really nicely. So when they shot the electrons at the crystal to check to see if they actually refract, well, the crazy thing is it actually worked, which is unbelievable. And of course, this was really important because it actually showed mass actually has a wavelength when it actually moves. So there's no restriction on the mass. So this means that any mass in motion actually moves with a wavelength, whether it's an electron, a proton, a baseball, a car, a plane. But the thing is, with Planck's hypothesis in the numerator, the wavelength is so microscopically small you'll never actually notice it. But it showed that everything actually moves as a wave. So the big, huge thing about this is not only is duality a light thing, but it actually showed that duality actually applies to everything. Okay, everything has both particle and wave attributes, which is unbelievable. And this is the beginning of quantum mechanics. This is where quantum mechanics really kicks in. Okay, so let me show you something that's really kind of neat. When you guys first start really looking at atoms and what atoms look like, you often see images like this. Actually, I'll move this down a little. Well, it's okay. Stuff like this, which is just a general cartoonish type model. Okay, you guys are shown this type of stuff for how things link together. When you actually start looking at actual pictures of actual atoms, you start seeing images look like this from like scanning electron microscopes and stuff like that. When you start going deeper and deeper in detail and theory, you guys might look at orbitals, that type of stuff. But when you actually start looking at actual images of actual atoms, this is taken the scanning electron microscope, these are pictures of atoms. And what you can see is you can actually see the ripples in the waves because the electrons are moving around the nuclei, not as particles, but electrons move as waves, just like everything does. And you can actually see the wave interference patterns. You can see a whole bunch of ripples and stuff like that as the electrons are moving around. And this applies to anything. So it doesn't matter if you're talking about these atoms or the atoms in your table or the atoms in you, they're actually collections of wave formation. So you're actually made up of waves and rippling waves and that type of stuff. Okay, here's another picture of a whole bunch of atoms that are like in a ring and stuff like that, and you can see the interference patterns, you can see the ripples, you can see lots of cool things. So it's really cool how this duality stuff sort of kicks in and extends to absolutely everything is actually made up of these combination of both particle and waves. And everything is basically made of wave formations. And when the electrons are actually going around the nuclei as waves, and go back to like this picture, when they're going around, it's not just random. Like the size of the orbits are not random, because not only do they go around the nuclei as waves, they actually do it as a standing wave. So you guys took standing waves in grade 11 and that type of stuff. So when the electron's going around the nucleus, it actually has to create a standing wave formation. And if I go back to a picture, there we go. You can see that the waves actually have to fit, and this is really the beginning of quantum mechanics. So the waves of the electron waves, as they're going around, they actually fit perfectly. The wavelengths have to fit perfectly to create the standing wave formation and create those nice orbits. And this applies to everything. So you are made of standing wave formations, your car is made of standing wave formations, everything's made of standing waves. And so the duality thing connects to absolutely pretty much everything in existence.